So welcome back, everyone. We have another edition of Symmetry in Newcastle, and the first speaker of today is Sven Raum from Stockholm University, and he'll be talking about locally compact groups acting on trees, type 1 conjecture, and non-amenable von Neumann algebras.
Yeah, thank you very much, and thanks for interest in this older work. I'm kind of happy that that people still look at this, and I must say, like at some point, I meant to work on in this direction, but somewhat got distracted by other projects. But it's a good motivation for myself to look into these old things again. So I want to explain to you how operator algebraic tools can be used in order to understand more details about representation theory of, in this case, specifically groups acting on trees. And like during the preparation, I must say, like I hope I found the least square approximation in terms of like what I can expect people to know, because I expect a group theory background, but not necessarily unitary representation or an operator algebra background. But I hope I pitched this correctly. So right. So the objects that I'm going to talk about just quickly are going to be groups acting on trees, and more specifically, what I mean is T for me is usually a locally finite tree, and let's say G usually should act properly and simplicity on the tree, so that I have a locally compact group. As an operator algebraist, it's very convenient to have locally compact groups, because otherwise we don't have like kind of canonical operator algebras. There's no regular representation that we can work with. So I work naturally in this setting. I'm aware that other settings might be interesting, but for an operator algebraist, this is the natural thing. So particularly if G is, let's say, really acting faithfully, let's say closed, then this is totally disconnected. So this is the kind of groups you are generally interested in. Okay, so let me recap a few examples. So this is the setup here. I will come to the question in a second, but let me just mention a few examples that I would keep in mind. Of course, out T itself, the full automorphism group, that's a standard example. Like discrete groups, well, let's do it differently. First, if you act by reflections, you could generate a copy of a free product of set mod 2 sets inside the automorphism group of an n regular tree. And inside you find an index 2 subgroup, which is just a free group. So I guess the free groups are standard examples of groups acting on trees. And otherwise, I guess you all know Barthes theory. So free products of groups usually can be made acting on trees, let's say of finite groups, then the tree is locally finite. Okay, so more generally, you might think of amalgamated free products such as PSL2 sets. But then there are algebraic kind of objects like rank 1 algebraic groups over QP, for example, that would act on a tree. That's the rank 1 case of TITS buildings. And what I find personally interesting is more the combinatorial part, like Burger-Mozes groups. And I will just very quickly recap what this is, because in this case, I really don't know who in the audience knows Burger-Mozes groups or not. I'm sure there are a lot of people who do, but I suspect that a few might not know. So Burger-Mozes groups, I personally find them very interesting because they, okay, maybe I come to the motivation in a second, but they give kind of a really original class of groups acting on trees compared to other buildings, right? So on other buildings, you cannot as easily define groups like of that kind. So let me explain what Burger-Mozes groups are. And so the F here, I'm sorry. After the holiday break, one needs to get used to writing on a tablet again. Burger-Mozes groups I wanted to explain. Okay, so F here is a permutation group, okay, and then UF in the end will be a subgroup of the n-regular, of the automorphism group of the n-regular tree. And we have to decide in some way whether an automorphism belongs to this group or not. And this will a priori depend on a labeling. I mean, in this case, edge labelings. Let's say I take the following example here. Around every vertex, I would label my edges in such a way that I get a bijection with our given set. So I took 3 here. That's the smallest interesting case, somewhat interesting case, which is non-trivial to draw and trivial enough to draw. So now I have a vertex V here, and I say we have a G given, and let's say it maps this vertex here. Then now you can have a look at this neighborhood, which is mapped to this neighborhood around the vertex, okay? And this means that we can define a permutation, right? So in the end, we decide to say that he is in in UF, if and only if for every vertex, we know that this map here belongs to F, and we should call it, maybe let's say alpha of G at V, the local action of alpha at V. That's an element of Sn a priori. And I want that this belongs to F for all vertices V. Okay, so in particular, if you fix a vertex, you're supposed to permute the edges just according to F. No more conditions on the element. Okay, and these groups are particularly nice. They have this so-called Tits independence property, which makes them very combinatorial in nature. Okay, thanks to what is called Tits independence property. Very combinatorial in nature. Okay. So this is one example of groups that I would like to also keep in mind. And now comes the question, like we have a few examples. I prescribed the setup, and let's first ask, why should we study groups acting on trees? Why should groups trees be studied? Probably this question is not new for you. I want to simply tell you my perspective on this question. So definitely there's some history of the topic, like lattices in trees. That's a classical thing. Like the work of Burger-Mozes was producing very interesting new classes of groups, like finally presented simple groups, like by looking in this case at products of trees. So there's a rich history, right? I mean, like rich and successful history of studying such groups. Yeah, but that gives just like an authority-based justification of study, but not a direction. For me, two things are important here. First of all, I have a much richer playground compared with other setups. I like trees are, let's say, rank 2 buildings. I take a rank in this case, that's the number of generators in the Coxeter group, are rank 2 buildings for which so studying groups acting on trees is part of a bigger quest to understand the symmetries of highly structured geometries. And in this setup, maybe I just should mention orally that I see this somehow as a 2-dimensional grid. On the one hand, like if I increase the rank and go from affine to non-affine for buildings, then I can get interesting groups which go beyond like what people study, for example, in classical algebraic groups by going beyond affine buildings, right? So this is one way I could go. For example, I worked like over the last year, maybe a bit more on right-angled buildings, which have higher rank if they're not trees. And you find interesting automorphism groups there and interesting groups acting on such buildings, also from the point of view of operator algebras, as I will put, as I will explain in a second or a little bit later. But on the other direction, you can also like just keep one type of building and say like, okay, what happens if I kind of connect the geometry to the tree, the geometry to the group in different ways. And the strongest version would be like strongly transitive actions, which very much link the group to the building. And there, trees are special because we can have strongly transitive actions without being right away basically of algebraic nature. So this is a result for affine buildings, so that if you act like strongly transitively, then the building basically comes from an algebraic group, and the group itself is somewhat apart from a Galois group plus an algebraic group. So you don't find extremely new examples. And I just showed to you with the Burger-Mozes group that this is different for trees. So I have more interesting examples to put in a theory and to develop my understanding of, like, let's say, representation theory of groups beyond algebraic, the algebraic set. Okay. And right now I just basically mentioned the other part, like trees in this way give a large realm of interesting groups. And this is a term that I got from one part of George Willis' papers, like this Cabras microcosm. I like the term somehow. It's Cabras microcosm. Oh. Allows to develop general understanding of TDLC groups by investigating groups acting on trees. So the philosophy is there simply like the class of groups acting on trees is rich enough to reflect major aspects of a general theory. Okay. And my focus here will be representation theory. I want to understand unitary representation theory of different types of groups. And in this case, I will talk about groups acting on trees. Okay, so there we get some interesting phenomena. Putting that in the context of what I said here with these buildings, like we know algebraic groups are all of type 1. I mean, at least over characteristic 0. And over trees, I have new types of groups. So a priori, it is not clear how their representation theory behaves. And then there was this classical question of Nebbia that I will recall in a few minutes, that asked like, okay, maybe there's a very clean geometric reason, namely a strong transitivity of the action, that gives you right away like type 1 groups and even stronger admissible groups. But from my perspective of an operator algebraist, I mean, type 1 is very nice, but I'm also interested in classes of groups which have more exotic representation theory where classical tools do not apply. So that led us to understanding or trying to understand how groups acting on trees can be actually put in different boxes where one can not only say if the group acts strongly transitively, then it is type 1, but I also wanted to know, like, is this sharp? Can we say, like, if the group does not act strongly transitively, and we have some minimal assumptions that don't trivialize the situation, can you find a very specific reason why this fails? So this is a philosophy behind the article at the time. So before going to representation theory now in more detail, let me just check the time. We started, okay, good. So I want to quickly recall a few words about, or a few things about unitary representation theory, simply because there I was not very sure how much background I can expect. So let's say if I have okay, how do I want to set this up? Sorry, let's write the topological group. Then I can associate with that, like, let's say we have a Hilbert space. Here, always complex. Then a unitary representation of G is a continuous map G to pi of H that is G, or Gi converging to G implies Gi psi converges to G psi. And I should not get implicit for all psi. So I ask for pointwise convergence. Okay, so this is just kind of the minimal type of connection that one would like to have. And if G is locally compact, the Haar measure allows to define lambda from G to L2 of G, and that's just the linearization of the left translation action, right? So lambda G psi at H is psi to the -1 H for all, let's say, compactly supported continuous functions, and then this extends to unitary representation. Okay, so this way we get a canonical representation, and this one will be the basis for defining operator algebras a little bit later. But before going there, I want to explain you what is actually, or what do we understand by good representation theory, and this is one thing about admissible slash CCR representations. So let's say admissible representations is something that originally comes from Lie groups and algebraic groups, but one has a very nice way to define it for general totally disconnected groups. Okay, so an irreducible unitary representation. Irreducible means like you cannot split it up in a direct sum, which is actually the nice thing for unitary representations, like indecomposability is equal to irreducibility, right? So as you don't get any non-semi-simple phenomena. So an irreducible representation, let's say pi of TDLC group is admissible if for all compact open subgroups the set, these are all k fixed vectors, let's say for all k in k, pi k psi, is finite dimensional. Okay, this is, as I said, like it's a classical condition from algebraic groups in their representation theory, and the significance of this type of definition or this type of representation is that we have algebraic means to understand them. So maybe a little bit, if I would say I have a uniform bound on such dimensions for arbitrary unitary representations, or let's say even in their situation not necessarily unitary, right? Then suddenly if I look at suitable algebras of operators acting on such, then I can describe them as almost commutative rings. Okay, so they have, like, if this is uniformly of finite dimension, then I have a certain matrix algebra part, and for the rest a commutative ring. So suddenly things are available. I mean, tools from algebraic geometry get available. That's the reason why this notion is important. Okay, and the same reason applies for unitary representations and for general totally disconnected groups. As soon as I know that something is admissible, I have a good chance to use finer tools to study these representations. Okay. There's a different notion from coming more from operator algebras. The representation is called CCR if, and now I should beg your pardon for stretching the notation a little bit. Oh, I'm sorry. If taking this representation, I can define how I want continuous functions with compact support on the group, how they should act. If this one is, these are compact operators. One H. If this one acts by compact operators. And I mean, I didn't introduce any operator algebras yet, but if you have a little bit of a function analysis background, then you probably understand like compact operators that somehow corresponds to operators that we can describe by discrete data. Like they should be considered as a little bit of quantized versions of C0 sequences. So we can very much understand what's going on there. And like one theorem, now my slide is a little bit, this follows from work of Klim in the 60s, says like a group, a TDLC group, let's say, in this case, because I defined it like this, TDLC group is admissible if and only if it is CCR. So in the sense that every unitary irreducible representation is admissible if and only if every unitary irreducible representation is CCR. Okay, so we have a good operator algebraic way to express a classical criterion from the study of representation theory of algebraic groups. Okay, so that's one consequence. Yeah. Okay, so now it's time to state what Nebbia proved. So this is about the admissibility conjecture. And I will comment about one mismatch in, I mean, here I call it the admissibility conjecture. In the abstract, I wrote something about a type 1 conjecture, so I will say something about this in a second. So what Nebbia proved in 1999, Nebbia, Claudia Nebbia, we worked a lot on groups acting on trees. So if G is closed in out T, is a closed unimodular meaning that the modular function is trivial, like your standard Haar measure is left and right invariant. Okay, this is a condition. Yeah, I mean, I can explain you maybe in a second why. Closed unimodular and admissible. A group acting transitively on vertices. Then G acts transitively on the boundary of T, and this is in this case equivalent to being strongly transitive, meaning like acting transitively on pairs of edges and vertex that is contained in the edge. Okay, so this says like if a group acting on a tree has nice representation theory, then it must act already transitively on the boundary of the tree. Okay, this is what he basically proved. Now, this should be put in a bit of a context, like compare like the boundary of T. This is the same as like G mod a Borel group for like G equals PSL 2QP and B the Borel group of upper triangular, I mean, of our triangular matrices. So it basically tells us, okay, like in this setting where we don't necessarily come from any algebraic, I mean, where we don't have any algebraic origin, a certain type of structure, like the importance of the flag variety in this case, persists, but in a different shape. So we have to think simply about the boundary of the tree. Okay. So now his conjecture was that the converse should hold. The converse should hold. Like this means like if I have a group that acts transitively on the boundary of the tree, then it should be already admissible. Okay. Okay, what should I say about that? Right, I mean, like there are different versions to formulate that. So if I formulate like this, like transitive action on the boundary of the tree implies admissibility, I could possibly have compact groups in my scope, right? I mean, like if I fix a vertex, I can still be acting transitively on the boundary of the tree. But compact groups have a very nice representation theory. So this is not an issue. That's just a matter of the right formulation. So if you have seen a slightly different variation of that conjecture before, they are equivalent. Okay, so that's just like a convenient way to formulate it right now. Okay, so this is, I mean, personally, I think this is now thanks to the richness of groups acting on trees, and this was at that time not really known. I mean, this is before Burger-Mozes came up with their groups, for example, right? I mean, Burger-Mozes is the beginning of 2000s. Considering the richness of the class of groups acting on trees, this is actually a fairly like interesting statement. Like it could be that despite that there are many examples that we cannot just classify or understand like their very algebraic means, nevertheless, there's one geometric reason why they should have all good representation theory. Okay. And I take a new slide. I'm writing a little bit too long for the slides here. Verified 4. So like obviously algebraic groups, like this is just classical, but then out T, that was I think this is the way to write him, and that was in the 80s. Sorry, I don't remember the year exactly. So he, I mean, what Olshansky did at the time is observe like the methods from the representation theory of algebraic groups also somewhat applied to out T. So he could, in a sense, classify representations and see like, so this admissibility conjecture holds, although it was of course not stated at that time, but it's told. Then Burger-Mozes groups. This is in a sense work of a student of Marc Berger, Aman, 2003, in his PhD thesis, basically did the classification of unitary representations, and Corina Ciobotau wrote down how this classification implies that the groups are actually not only admissible, but this notion that I alluded to, that one has a uniform bound on the dimension of these fixed points, that's called uniformly admissible. Okay, so this one can prove, and it holds also for algebraic groups and out T, by the way. I mean, like, and more recently, a student of Pierre-Emmanuel Capras, he verified this conjecture for certain examples constructed by another student of Pierre-Emmanuel, Nicolas. No, not writing well today. Nicolas Radu. And this was Lancelot Semal this year. He basically pushed further the ideas of Olshansky, and that also were used in Aman, and now really developed a little bit more of an abstract approach. In which situations could the ideas of Olshansky actually be applied to some group acting on a tree? And he has actually a quite nice language that he develops in his article, and then can conclude specifically, I mean, for many different types of examples, but specifically for these groups of Nicolas Radu, he can conclude that type 1 conjecture holds, the admissibility conjecture holds. Okay, now there was this slip with type 1 conjecture. This reminds me that I promised to explain why is there this difference. I must simply say that it's some time ago that I worked on this. So when I wrote the abstract, I had forgotten that there was some insight in the literature that I had after writing this article. Namely, when writing the article at the time, I had heard about Nebbia's conjecture from Tim Steger. He mentioned that at a conference in Spa in Belgium during my PhD still. That was 2012 or so. And that was my resource. And only later, I mean, and as far as I remembered, he mentioned type 1, which is a slightly weaker statement. And then later I've searched the literature. I should have probably done this when writing that article, but I admit that I didn't. So I found this article of Nebbia because I was interested. Okay, what actually literally did he prove? And found that he actually stated admissibility. Hence the discrepancy. When preparing the abstract, I forgot that I had learned this in the meantime, and just wanted to state the things as Nebbia actually wrote them down. Okay. Okay. Good. So much for what happened before. So now we are at a state where we know, okay, there are certain groups which do not have nice representation theory, namely those which do not act on the transitively on the boundary, and we have a whole class of examples for which we do know more. I mean, we know that the representation theory is nice, and now operator algebras come into the game, and we want to make a little bit more precise. Why does this conjecture I mean, how sharp is this conjecture, maybe? And second, why would a group like fail to have good representation theory? And third, maybe I will have time for that or not, to be seen. How can one go on? Maybe there are operator algebraic tools one could apply in order to prove actually this type 1 conjecture. Okay. And I mean, there are some ideas around, but as I said, somehow this project was a bit dormant over the last years. Okay, my main tool will be group von Neumann algebras. So the group von Neumann algebra for a locally compact group is simply we take this left regular representation, and then with prime, I will define this formally in a second. I mean all operators that commute with this whole set. So if I just put the prime here, this would mean the algebra of intertwiners, right? The endomorphism of this, the endomorphism of that module, L2 of G, but I take twice this commutant. Okay, and then I get an algebra that clearly contains this left regular representation, but it contains certainly its linear span, but also much more. It's equal actually to this integration and then closing in the pointwise topology, where SOT refers to the pointwise topology. So let me explain these two pieces of notation here. So what do I mean with this? Like if S is in the bounded operators of some Hilbert space, then with S commutant, I mean, let me write it in script form, the set of all T in B of H, such that for all S in my script S, I commute TS equals ST, right? This is the commutant. So if you commute with all elements coming from the unitary representation, then you're then you're an intertwiner of that representation, right? So the one commutant would describe the endomorphism, and then I take the second commutant to come back to the other side. Okay, I could, and maybe this is informative to interpret this, I could equally well define this by a right regular representation and just take one commutant. So the group von algebra is the algebra of intertwiners of the right regular representation, if you like. Okay, just to put this into a context. So we are not looking at anything like completely exotic. It's just like rather large because we are acting on a Hilbert space. But as an abstract object, it's just an algebra of intertwiners of a representation. The other thing here was this SOT. This is the topology of pointwise convergence. On H, or in this case, sorry, on L2 of G. Okay, so I used this before when I defined unitary representations. It's a very useful and kind of elementary topology that one uses as an operator algebraist, and it has this name, strong operator topology. I mean, every field has its own names, so that's fine. So we have two points of view on this algebra. Okay, maybe exactly in view of the time, let me mention some examples. I'm interested in a property that is called amenability, and that means I will now just look at this algebra and tell you how does admissibility somehow get reflected in there, and then tell you, okay, there's a property called amenability, and if I negate this, then I get a very strong negation of being type 1 / admissible. Okay, so an example of von Neumann algebras that means like an algebra that satisfies such a bicommutant equality, an algebra that is equal to its bicommutant, they would, besides LG, include things like taking a measure space, or a space equipped with a measure class, and taking essentially bounded functions on that space. Such an algebra would be a von Neumann algebra, for example, and it's a rather easy one. Similar, I could take simply Mn of C, right? Or just the full algebra of operators on a Hilbert space. And I intentionally have now just 3 examples, like something that is a little bit elusive, and 2 which in a sense are rather trivial, right? I mean, like L infinity of x, okay, that's functions, right? We believe that we can control functions on a measure space in a sense. And we also believe that we understand matrices rather well, and the same to a certain extent can be claimed about bounded operators on a Hilbert space, right? Now, the notion that links admissibility and von Neumann algebras is type 1 groups. So a von Neumann algebra is of type 1, let's say I call it M, if, oh no, I don't need to, if it is isomorphic with a direct sum, let's say over certain cardinals, and I take for each cardinal 1 measure space and tensor it with the bounded operators on L2 of kappa. Okay, like for suitable measure spaces. X kappa. Okay, so ultimately this should be 0, of course. Like I'm a little bit sloppy here in terms of cardinalities, or in terms of well-definedness, taking a direct sum over all cardinals. But let's say typically we would get a direct sum over some measure space, tensor matrices, plus another measure space, tensor larger matrices, and so on, plus L infinity of yet another measure space, tensor B of L2 of n, the natural numbers, right? That's a typical case. For a second countable group, this would be all. We don't need to take into account all cardinals. Now, this is kind of the down-to-earth definition of a type 1 von Neumann algebra, which just clearly exposes these are the easiest type of von Neumann algebras we could have, right? And then we call a group is, I mean, group G is type 1 if pi of G is type 1 von Neumann algebra for all unitary reps pi. And again, Klim, I cited him before, says like admissible implies type 1. And I mean, like that really needs some work in this case, but it shows us that we have, if we are admissible, then the only von Neumann algebras that we generate by unitary representations are rather easy ones. Okay, like can be described by a very down-to-earth. And now the whole point is find out how you could negate this. Okay, idea, obstruct type 1 by so-called non-amenable von Neumann algebras. And here's a source of non-amenable for algebras without ever defining what amenable this point means, like G discrete, then G is amenable just as a group if and only if LT is amenable. And the example we should have in mind is L of F2, right? So this is, by the way, it's a question, like as I said, without having defined it, but does every non-amenable von Neumann contain a copy of LF2? That's the von Neumann-Algebraic de von Neumann problem. Like in many situations, it does not have a positive answer. For von Neumann, it's completely open. We don't know. So in general, it's not true that for non-discrete groups this implication holds. Like out T, for example, is a counterexample, right? I mean, out T we said, I mean, it's definitively non-amenable, but we said like it is admissible. So in particular, this is type 1, and I explained to you like type 1 would imply amenable. So now let me come to a theorem like. No, always order. This was published in 2019. What we proved with this idea is that if T be locally finite tree and G in out T be a closed non-amenable subgroup acting minimally, on T. And if T does not act locally too transitively, then LT is not amenable. In particular, G is not type 1. Okay. And what does locally too transitive mean? Like it means like if you look at a vertex stabilizer, you would act too transitively on the vertices, on the edges attached to that vertex. Okay, so this would mean locally too transitively. And the examples, UF is locally too transitive if and only if F is too transitive, if and only if UF acts transitively on the boundary. Okay, so for the UF, one now has a good characterization of like when they have good representation theory, and one has a good reason why they are not of good representation theory in case they do not act transitively on the boundary. Namely, the group von algebra is actually non-amenable, and more concretely, I cannot really show you the proof here, but we produce concrete copies of free product von algebras which show non-amenability in this case. Okay, like it's a pity that for the time I cannot really go very much into the details of proofs, but I just want to state one. Oh, well, maybe it's better to. I mean, I will refrain from stating a conjecture, but rather explain you very quickly what's the idea, how to produce this, so that you have an insight what happens actually here. Idea of proof. Okay, so let's say G edge transitively, transitive and type preserving. So then G is actually an amalgamated free product over an edge stabilizer. That's Bastiat's theory. Okay. And that also gives us an amalgamated free product decomposition of the group von algebra. And what we will do, or what one does, is that inside LG, one finds a certain compression with Hecker algebras. Now come on. Let's say G, no, GE. Not right. Okay, so one finds a certain Hecker algebra in there. Okay, and so these are Hecker algebras. And everything one has to do now is observe that GV, let's say, acting on EV is conjugate to GV acting on, I'm sorry, I want to have in this case GE, GV modulo G. So the Hecker algebra will give us a free product where we have this here. Now, how does the edge stabilizer act on the neighborhood? Well, I mean, we have a stabilizer already, and it's going to have two orbits here exactly if the group is locally two transitive, right? That's just two transitivity. So this is going to be at least 3 if G is not locally two transitive. And we observe that like M free product N, this is a von algebraic result, is non-amenable. It's basically a free product. I mean, it's basically L of Fn for some free group N. I mean, basically non-amenable if dim M is at least 3, dim M is at least 2. And this way one can really concretely, thanks to this observation that local two transitivity translates into a size condition for such Hecker algebras, apply basic von algebra. I mean, basic. I mean, this is really free probability theory. One has to really work for getting such a result, but it's kind of classical. Still, one can apply such result and clarify some things about representation theory for these groups. And you see, like, this is of course like just scratching at the surface. Like the long-term plan would be to understand better such amalgamated free products, and one can formulate these questions in a von algebraic language, where one can split up the problem of the admissibility conjecture into a part where one has a purely von algebraic problem about so-called amalgamated free products of discrete type 1 von algebras, plus a problem about how irreducible representations from an edge group induce to irreducible representations. I mean, induce to a decomposition of irreducible representations of a vertex group. So basically one gets a problem. I mean, one gets a split of the problem, which I personally think could be an attractive way to attack this problem of the admissibility conjecture, not only in the negative, but also in the positive direction, really. And I think I'm a bit over time. Thanks for your patience with that. And thanks for your attention.
Thank you, Sven, for the talk. It's really nice. Do we have any questions? Well, it does not seem like we have any questions for Sven. So yeah, let's thank Sven again.
Thanks.
And we'll reconvene after the coffee break.